Welcome back for some extra notes and review of chapter 4.1, which is all about systems of linear equations in two variables. So when two linear equations are graphed in the same system, there's three possibilities. They could either intersect at one single point, such as case one. They could be parallel, which means there's no solution. They have the same slope, but different y-intercepts. Or case number three means that they're essentially the same line. And so there's infinitely number of solutions because one is just a multiple of the other. It's like doubling a recipe or tripling a recipe. They're also described here. So case one, they intersected a single solution, x and y. Case two, we consider them right here to be inconsistent because they're parallel, they never touch. And case three is they're considered to be dependent because they're essentially the same line with infinitely number of points as solutions. So there's two methods that we have learned in lesson chapter 4.1 to solve these systems of equations. One of them is the addition method. The addition method sets up so that we will add the two rows together to eliminate one of the variables. And you kind of want to be strategic in which one you choose because it might be easier to manipulate one row or the other in particular. So as for this first one here, I'm not going to go through them all, but this first one here, we can see that x has the same coefficient, a -1, but they're the same sign. So for us to be able to add the two rows and eliminate the x variable, they need to have the same coefficient but be opposite signs. So if I take a -1 of row 1, it will create row 1 to have opposite sign of row 2 on x. So it'll be a positive x plus y equals a -4. And if we keep row 2 the same, notice how I'm noting what I'm doing, all of my instructions. Those are expected for you as the student to show the reader. Row 2 is staying the same, so that now the x coefficients are the opposite signs, but the same coefficient, so they add to 0. So I'm left with 3y equals a -7, and I can solve for y. Once I know y, I can substitute y back into either row 1 or row 2 to solve for x. Let's do an extra problem here. Letter D. I have 3x minus 4y equals 7 and 6x minus 3y equals 5. So I can see that on the x, row 2 is a multiple of 3. So 6 is a multiple of 3. So I can multiply row 1 by 2 to get to a 6, but I need them to be opposite signs. So I'm going to multiply by a -2 to row 1. So this will become a -6 plus 8y equals a -14. I'm going to keep row 2 the same. Now when I add them, the 6x and -6x terms add to 0. And I'm left with a positive 5y equals a -9. If I divide by 5, I get y equals a -9/5, which is the same as a -1 4/5, which is the same as a -1.8. And we're going to show this in Desmos. So now that I know that, I can put that back into, say, row 1. So I know y is a -1.8 equals 7. So 3x plus 7.2 equals 7. If I subtract 7.2 from both sides, we have 3x equals a negative 0.2, and x will be equal to a negative 0.2 divided by 3. And I'm going to go to Desmos to solve this piece, or my calculator. Okay, so in a decimal form, this is going to come out to be a negative 0.0667. So when we go to Desmos, we will be able to see that we can turn this quickly into a fraction. I'm going to do a new share into, and we'll go to our Desmos screen here. And a negative 0.066. I'm going to just see what that fraction comes out to be. So 33 over 500. So it looks like it's 3 over 50 or so. So, okay. So let's put in our system of equations. 3x minus 4y equals 7. And then we had 6x minus 3y equals 5. And I'm going to zoom in here so that I can see where they intersect here. They intersect right here. So the decimal that we got, the same thing, a negative 0.067 and 1.8. Now remember, I am encouraging you to use Desmos to find the solution up front, because then you know what you're working towards. Why not? So the second method of solving a system of two linear equations and two variables is called the substitution method. This method is nice when you already have one of your variables solved in terms of the other, kind of like a recipe already using one variable. Then you can use that to substitute in for the second. So I'm going to go through an example that we did in. So example A here, we were given y equals 1/2 x minus 2. And then the second equation is 2x minus y equals a negative 1. Since we already know how to make y by using 1/2 x minus 2, I can substitute that piece into my second equation. So it still looks like 2x minus y equals a negative 1. 2x minus, right here where my finger is, this y is now going to be 1/2 x minus 2. Notice I put it in parentheses because I have to make sure that I distribute this negative properly. So when I do that, I decided to multiply through by 2 to eliminate my fraction. So that's why we multiplied by 2 here, by 2 here, by 2 here, and by 2 here. Eliminating fractions was something we decided at the beginning of the semester would make our equation solving much more simple. So let's look at an extra problem here, letter D. So back to a fraction situation. So I know how to make y by using 3/5 x. So in my first equation here, I'm going to replace y with 3/5 x. So 2/5 x minus 2/3, and then this is going to be 3/5 x equals 0. And so those cancel out, and so I end up with 2/5 x subtracting 2/5 x equals 0, and those actually cancel out, so we get 0 equals 0, which is a true statement. but this tells us that it's a dependent system. They share every point. There is infinite number of solutions. Infinite number of solutions. And I'm going to show that by taking the decimals. I'm going to export these. So my first equation is the y equals 3/5 x. And then the other one is 2/5 x minus 2/3 y equals 0. And you can see that they're overlaid. So I'm going to zoom out and I'm going to turn off the red line and it's the black line because they're actually the same line. So that's how we know it's a dependent system with infinite number of solutions. Catch me back for other videos.